Okay, so I'll have a look at question 2 now. So this is Margot going bungee jumping. So she does a bungee jump, and after 2 oscillations she's bouncing up and down in simple harmonic motion, and we're told her mass, and we're told the angular frequency of her simple harmonic motion is 2.2 radians per second. Okay, so the first thing it asks you to do is calculate the period of her motion. So we know that time period is related to her angular frequency, and with that equation, 2 pi just a constant, and then her angular frequency 2.2 radians per second. So if we put that into our calculator, 2.86 seconds, and that's just simply a substitution, so it's only ever going to be worth and achieved for level 3. Okay, so the next bit then asks us to, it says Margot's boyfriend Mark uses the same bungee cord. The period of his oscillation is 3.5 seconds. So can we now use that to help us to calculate his mass? So if we're thinking about this, probably, I guess the equation that you're probably going to think about first is that T is equal to 2 pi m over k square root. So if we're wanting to calculate Mark's mass, it would make sense to use this equation because this has got mass involved and it's also got time period involved, which we've been told in the question here. The only thing that we don't know though is the stiffness of the spring. What was happening with Margot, we should be able to work out K for that particular bungee cord. Okay, so we can come back to that. So using the same equation for Margot, what we can say is that if we rearrange this to make K the subject, we end up with 4 pi squared over T squared. So we've got 4 pi squared multiplied by her mass, which we're told is 55 kgs, and here for her we had an angular frequency of 2.2. Oh, sorry, no, time period 2.86, and that's going to be squared. So if you put all that into calculator, you get 258.18, etc., etc. So that tells us the stiffness of the spring. So now we can go back and use the same equation for Mark. But what we want to know now is his mass. So again, we're going to have to rearrange this equation. We rearrange the equation to make mass a subject with this. So we can say, I think his period is 3.5 seconds squared multiplied by 258.18 from up here and divided by 4 pi squared, and I think that comes out to be 82 kgs. So actually this is one of those weird questions. There was no achieved part for this. For working out K, you got to the merit level, and then for working out his mass, that took you up to the excellence level. And then part C of this question was looking at what happens when Mark now cuts the bungee cord in half for some reason and joins them in parallel. He repeats his jump using the new bungee cord. Explain how the frequency of oscillation compares with his first jump. So he's joined them in parallel, so we start off with a rope with a certain amount of K. He's cut it in half and he's going to attach it like this. Now when he does that, and we've got essentially K in each of these, we've now got double the K. So if we add them in parallel, effectively we're doubling the stiffness. Okay, so we've got twice the stiffness here. So when we cut them in half, we're going to get double the K in each one, plus adding them in parallel doubles K. So effectively now we've got 4 times the stiffness, because we've got 4 times K. So if K is going to be 4 times bigger, if we think about what this will do in terms of the frequency of our oscillation, I guess first of all it might help to think about the time period. So you've got 2 pi over K, except now K is 4 times bigger. So if everything else stays the same and K is 4 times bigger, it makes our time period half. Okay, because remember this is square rooted. Okay, so that will halve our time period. Now if we remember, we looked at this in waves even, time period and frequency are related by the following equation. So if your time period is halved, your frequency will be double. So the frequency of his oscillation compared to his first jump will be double. So if you got to the fact that it's 4 times the stiffness, that got you achieved. If you said it causes the period to decrease, ideally, obviously we're going to be specific, so we want to say it would be half. That will get you up to the merit level, and the frequency being doubled, this last bit here, gets you up to the excellence level. So far question 2, not too tricky. I think when we got on to the second part of this, which is the circular motion part, I think that's when it started to get a little bit tricky for us, but we'll have a look and see how we go with this one. Alright, so Christina's also doing a jump. She's got a mass of 65 kgs, period of her oscillation 2.6, yeah, so we've got that and that. During one oscillation, Christina's amplitude is 3 meters and her lowest point is 1 meter above the water. How much time does she spend more than 3 meters above the water in one oscillation? Okay. So, her amplitude is 3 meters, so that means this length here is going to be 3 meters, and this length here is going to be 3 meters. And her lowest point is 1 meter above the water. Okay, so when she's here, she's 1 meter above the top of the water. How much time does she spend more than 3 meters above the water in one oscillation? So if she's more than 3 meters above the water, she's going to have to be from here 1 meter and then a further 2 meters up here. Okay, so if this whole length is 3 meters here, we're looking at having 2 meters added on here. So they want to know how much time she spends more than 3 meters above the water. So we've got to find out how much time she spends in this area and then how much time she spends up here. Okay, so if we have a look at how we might do that. Okay, so if we're thinking about this, I guess the easiest way to think about it is it's the same as time more than 2 meters above her lowest point. Okay, so from here to here we said is 2 meters. So how long does she spend more than 2 meters from her lowest point? So if you're thinking about the reference circle, it's, I guess, from going all the way around here and back to this point here. Okay, so if we draw ourselves our little triangles, okay, so we're going to be here, this distance here is going to be 1 meter. We know that this distance across here, the radius is going to be 3 meters. Yep. And what we're trying to work out then is, if we think about our little triangle here, we can look at going around the reference circle. Around we come in this direction, because remember we always go around here like this, and there we go, we've got an angle in there. So we've got an angle here which is, we've got a side here which is 1 metre, a side here which is 3 metres, and if we think about our trigonometry, we've got the hypotenuse here, okay, and we've got an adjacent side here. Oh, sorry, no, not that angle here. We're looking for this angle here. Okay, sorry. So we've got a hypotenuse here, and we've got this angle here, which is going to be your opposite side. So because we've got opposite and hypotenuse, we can say that sine theta is equal to opposite over hypotenuse, which is going to give us 1 over 3. And if you put that into your calculator, it's 19.26 degrees. Now, what you've got to think is that you're going to have exactly the same happening on this side as well. So we're going to have that angle here, and we've said we want to go all the way from here, all the way around our reference circle, and all the way back round to here again. So we know we've got 19.26 degrees here, and we're also going to have an identical angle on this side, plus we're going to have all of this angle here. So our total angle is 19.26 times 2 plus 180 degrees. Okay. So that's going to give us 218.5 degrees in total. Okay, so that would give us all the time that she spends moving through this angle, all the way through here, and all the way through this angle. That's going to give us the angle that she moves through when she's more than 2 meters above there. And then if you remember back to when we looked at the fact that we can equate the percentage of the circle that we've moved through to the percentage of the time period effectively. So we're just looking at the ratios. So the little t is what we're wanting to find out, and we're told here the period of our oscillation is 2.6, and that's going to be the same ratio as those angles, so 218 degrees over 360 degrees. So T is going to be 218 5 over 360 multiplied by 2.6, which gives us 1.6 seconds. So she spends 1.6 seconds more than 3 meters above the water level, or more than 2 meters below her, above her lowest point. The next bit asks us to calculate her maximum acceleration. Now, remember when you were looking at your equations that were to do with your reference circle, there were some special versions of the equation when you're looking at maximum velocity and maximum acceleration. And so for our maximum acceleration is given to us by A is equal to negative omega squared x. So what we've got to out first is what omega is going to be, and we know, or we should know, omega is equal to 2 pi over t. So we've got 2 pi over the time period, which is 2.6. That gives us 2.42. And then A is going to be equal to minus 2.42 squared multiplied by x, which is before the maximum acceleration will be your maximum displacement, and that's 3 meters. So it gives us 17.5 meters per second squared. Then F was drawing on the diagram. This bit here was an excellence question. So if you got something on the diagram correct, that gave you an achieved. If you got the correct angle, so if you got up to 218.5, that was merit. If you got the correct period, that was the excellence question. This one here, if you got the correct angular frequency, so if you got this far, that gave you an achieved. If you got all the way to our angular acceleration, maximum acceleration, that gave you merit. And then part F, on the diagram, draw an arrow to show the direction of the net force acting on Christina at the lowest point. Well, at the lowest point, you know that she is just about to accelerate upwards, because remember, at the lowest point, we know the acceleration is always towards the equilibrium point. So she must have acceleration in this direction. If she's got acceleration in this direction, there must be a net force acting in that direction. So having the net force pointing upwards above her, or somewhere around here, F net, that got you achieved, and it was just an achieved question for drawing that on. Okay, so part G, gosh, there's one more part as well. Calculate the size of the acceleration and the net force acting on Christina when she's 1 meter above equilibrium. Okay, so there's a specific point here that they're looking for, and they want the size of the acceleration and the net force here. So when we're thinking about net force and acceleration here, we know that F is equal to mass times acceleration, and in this case acceleration is given to us, as we've said before, omega squared x, and so if we substitute those in, we end up with F is equal to mv squared x. We know that her mass is 65 kg, so we've told that in the question, and we already know that W is 2 pi over 2.6, which we worked out before, that's squared. And this is, and if you plug all that in, we get to 380 newtons. So we got the acceleration correct, which you probably should have, because you should have got it right up here. That's, yeah, so if you plugged that in correctly and got something in here correct, that got you achieved. If you got the full answer for the force, that got you merit. The very last part on this question should have been relatively straightforward. It was just a little piece of drawing that we had to do, but it was pretty woeful. This was just talking about damping effectively. So it said there's a significant energy loss due to friction as she continues to bounce. On the axis below, sketch a graph of her amplitude against time for 3 oscillations, and it told you values were not required to be marked on the axes. Okay. I think though they have given you some values here, so it would be wise to start, I guess, at one of these. So looking at how much space we've got 3 oscillations to fit in. So you don't want to make it too, probably don't want to make it too wild and big, but what we've got to do is show them that you understand that the amplitude is going to drop off, but the time period, so the time you've got between these maximums and minimums is going to be the same. So if we've taken 3 here to get all the way to the bottom and all the way to the top, sorry, that's actually not very well drawn, let me start that again. Yeah, it's just a case of trying to work out how you're going to squeeze these in. I'll probably make it a little bit tighter than that. So if I go, I'm going to put them at the bottom of my curve here, and then we're going to go up to the top. But what you want to do is make this maximum amplitude a little bit smaller, and you're going to come down. This one wants to be, again, not quite so high, so you're going to come down maybe to about that height, and then as we go up again, you want to show that the amplitude is decreasing again, and then down here that should be smaller than the previous one. Okay, so and then back up something like that. So what you can show is that these amplitudes are getting progressively smaller, and that's what they're looking for achieved. And then for merit, what they're looking for is that this time period is equal, because the really important thing is that the damping only has an effect on the amplitude, it doesn't have an effect on the time period. So if you can show them an equal time period for the 3 oscillations, that gets you up to level. So question 2 quite lengthy, but there's quite a lot in there. But there was also quite a few easy marks in there, I think.